Okay, for what we have regarding Laplace transforms, now we looked at degrees in t that were integers, or in this case natural numbers, and there's a pattern that will ensue for what we have in the case of what we have for all degrees in t. And we have for the Laplace transform of t to the n power, you want to have t goes from 0 to infinity, e to the negative st times t to the n dt. And for natural numbers, you would have automatically n factorial all over s to the n plus 1. And for other values, okay, we can apply the gamma function of n plus 1 all over s to the n plus 1. Now, when we looked into the gamma function, okay, now we had like gamma 1 is equal to 1, gamma of 2 is equal to 1, gamma of 3 is 2 factorial, gamma of 4 is 3 factorial, and so forth. And for fractions like gamma of 1/2, we had the square root of pi. That of 3/2, we had the square root of pi over 2. Now, for what we have in the third case, all right, so we have f of t is equal to the square root of t to the third, which we have at t to the 3/2. And just to kind of lay a foundation before I use this particular algorithm. Now, going back to what we have with the improper integral, where we have e to the negative of the square of the variable we're integrating over, as that variable goes from 0 to infinity. Again, the outcome we have at the square root of pi over 2. And let's say that if we use as a foundation, okay, we have f of t is equal to t to the negative 1/2. And for the Laplace transform, you would have, as t goes from 0 to infinity, of t to the negative 1/2 times e to the negative st dt. And if we look at this through the lens of integrating, okay, and so we have kind of complex here. We have with using substitution. Say if I were to have u equal to s times t, and then take the square root of the relation, we have u to the 1/2 is equal to s to the 1/2 times t to the 1/2. And taking the differential on both sides, I have 1/2 times u to the negative 1/2 du. And with respect to t, I have 1/2 times s to the 1/2. And t drops to the negative 1/2 power. And taking what we have in this particular layout, so we have u to the negative 1/2 times s to the negative 1/2 du is equal to t to the negative 1/2 dt. And so for what we have in the layout, okay, so writing what I have in terms of dt, okay, so I'm going to have in this particular regard, okay, so I have t to the 1/2 times u to the negative 1/2 times s to the negative 1/2 du is equal to dt. And just taking what we have now, okay, so we have in place of dt, so I have t to the 1/2, and that's going to cancel out t to the negative 1/2, so you don't have any t term present. And I have u to the negative 1/2, and I have s to the negative 1/2, and I have du to be applied. And in place of negative st, I have negative u. And okay, so this is what we have at the substitution stage. So I have equal to 1 over s to the 1/2 times the integral of u to the negative 1/2 times e to the negative u du. And applying substitution once more, so I can use this particular integral. And we can say we have v is equal to u to the 1/2, and we have that the square of v is equal to u, and taking the differential of the squared relation on both sides, I have 2v dv is equal to du. So we have in the follow-throughs, have 1 over s to the 1/2. And again, u to the negative 1/2 is going to be the multiplicative inverse of v, and I have times e to the negative v squared. And filling in for du, I have 2v dv. And what is going to happen here is that we'll have 2 over s to the 1/2. V to the negative 1 times v will cancel out. and we have e to the negative v squared dv. Okay, now again, going back to our improper integral, again utilizing f of t equal to t to the negative 1/2. So we have filling in, okay, we have 2 over s to the 1/2, and this time we have going from 0 to infinity of e to the negative v squared dv. So I have 2 over s to the 1/2. Now we have, in spite of the change in the variable, we had the same limits. So we have for the integral of whether it's x, t, or v, e to the negative of the square of the variable that we are integrating is going to have an antiderivative if the limits go from 0 to infinity of the square root of pi over 2. And here we're going to have, for this outcome, the Laplace transform will end up at the square root of pi all over s to the 1/2. And just sort of testing out what we had with our algorithm. Now we had f of t again equal to t to the negative 1/2, and using what we have for the Laplace transform. And again, so for t to the n, where n is situated at negative 1/2, applying the algorithm. Now we cannot have in the real numbers like the factorial of negative 1/2, but we can have the gamma function of negative 1/2 plus 1, and we had the gamma of 1/2 to arise, and we have all over s to the negative 1/2 plus 1, which we have s to the 1/2. And once again we have with gamma of 1/2, that was the square root of pi, and putting this back, and we have the square root of pi all over s to the 1/2. So we have consistency throughout. Now in terms of that remaining problem which we have to tackle, so we're going to have for the Laplace transform of the square root of t cubed, or in this case for what we have for t to the 3/2. So we will have the Laplace transform of t to the 3/2. So you have the integral as t goes from 0 to infinity, and we have of e to the negative st times 3 to, or t to the 3/2 rather, dt. And now factorials you can only truly work with natural numbers, but we can apply the gamma function. So we have with n at 3/2, so you have the gamma, and what's going to be 3/2 plus 1, and for s at the n plus 1 we have s to the 3/2 plus 1. So we're going to have gamma 5/2 over what is going to be s to the 5/2. For the gamma of 5/2, I have 3 times the square root of pi all over 4. And so just putting it, the final face, I have 3 times the square root of pi. And we have all over 4 times s to the 5/2. And that will be the result.